In this session, we will spend some time talking about the foundations of layer 2 networking. We will talk about virtual LANs, trunking, and spanning tree protocol, just the basics. Okay, so let's talk about virtual LANs. First thing I'd like to discuss here is the concept of a broadcast domain, which is basically part of the network that allows the devices to communicate locally at the data link layer and also reach each other for a broadcast frame. So this is when all those devices are part of the same broadcast domain. We can also call it a layer 2 network. Normally those broadcast domains or layer 2 networks are only separated by routers, so layer 3 devices, but it is also possible to provide the same isolation at layer 2 when dealing with the switches. You can basically use configure your switch so that part of ports, a couple of interfaces, you would put them into one VLAN, versus some other ports you will make them part of another VLAN, and this is gonna give you that isolation at layer 2. So a VLAN, a virtual LAN, is basically an equivalent of a single broadcast domain or a single layer 2 network, because all devices that are part of that VLAN can communicate directly at layer 2 without a need to route the packets by some sort of layer 3 device. So if I wanted to visualize that, we will have just two switches in this very simple network. Let's say that this is catalyst 1, and then we will have catalyst 2. Now we will now initially focus on just a single switch. Let's say that we have two PCs connected to this switch, PC 1 and PC 2. This is FO2, this is FO1. One of the devices goes to VLAN 10, and the other one goes to VLAN 20. So with this configuration, we can obviously add some more, configure other interfaces on the switch, make them part of VLAN 10, 20, maybe some other VLAN, depending on what you're trying to do. With this configuration here on this single switch, those devices, since they are part of different VLANs, they cannot talk to each other directly at layer 2. We would have to have some sort of external layer 3 device to route the frames between the VLANs, or we would have to enable switch virtual interfaces on this catalyst box. So it's going to be the switch that will be routing the packets between the VLANs. But normally without SDIs or an external layer 3 device, those devices will, the PC1 and PC2, they will not be able to communicate with each other. So this is a concept of a VLAN, a separate broadcast domain, single layer 2 network. Now what about if we have some other devices connected to the other switch? So let's say that we've got PC3 and PC4. Let's say that this is FO4, this is FO3, and one of those devices goes to VLAN 20, the other one goes to VLAN 10. We have two switches, 4 devices, and we want to allow communication between the respective PCs, I mean the PCs that are in the same VLAN. How can we accomplish that? If I were to say that we will interconnect our catalyst switches with a simple link that is configured as an access port, we would have to choose to either put it into VLAN 10 or 20, and then only the devices that are part of that VLAN would be able to talk to each other between the switches. So instead of interconnecting the switches with access ports, you would normally configure those interfaces. Let's say that this is FO5 and FO6 as a so-called trunk link. So this would cause the switches to form so-called trunk link, and the advantage of using trunks is that they allow you to distinguish between the frames that are part of different VLANs. Because the problem with this topology now is that when PC1 wants to talk to PC4, it sends the frame down to the switch. When the switch sends the frame to another switch, how is it going to tell the Catalyst 2 that this frame is supposed to be part of VLAN 10 and not, for example, VLAN 20? So there is no field in the original Ethernet specification that you could use for this purpose, and this is when those trunk links come into play. We have two trunking protocols, ISL, the legacy Cisco proprietary protocol, and an open standard, which is 802.1q. And those protocols allows they are configured on a trunk, and they basically allow to insert information about the tag value into the frame before the frame is sent for the trunk. So from this point on, when you configure the trunk, negotiated the trunking protocol or configured it statically, the PCs will be able to communicate as long as they are part of the same VLAN, based on the fact that we will be including the tag value in the frame. So when PC1 wants to talk to PC4, the frame is going to be tagged with VLAN 10. And when PC2 wants to talk to PC3, the frame is going to be sent with VLAN 20 over the trunk. So when Catalyst 2 gets the frame, it sees the tag value and is able to send the frame to the correct VLAN and to the correct device. So this is the concept of trunks. Now there is also a concept of so-called native VLAN, which is only relevant for 802.1q trunking, so that open standard version of trunking protocol. And this native VLAN describes a special VLAN on the switches that will be associated with the frames that were received without a tag value on a trunk, and also in the opposite direction, whenever I receive a frame on a port that is part of the native VLAN, I will be sending it over a trunk without a tag value. So we can say that we can configure our trunk with a native VLAN, which is supposed to match on both sides, so on both of the switches, both ends of the trunk. Like we can say that our native VLAN is going to be 50. So 50, 50, and we can use the same VLAN on one of our access ports, like PC5, and this port is part of VLAN 50. So when PC5 sends a frame, the CAT1 sees that the frame is received in VLAN 50, so it is going to send it for the trunk without a tag value. And on the other end, Catalyst 2 sees the frame without a tag value, this one, so it is going to send it to its native VLAN, which based on this configuration is 50. So they are generally supposed to match between the switches, the native VLANs, because you don't really have a situation when the frame leaks from one VLAN to another. But as a best practice, you should avoid using native VLAN on the access ports. So the trunk links, once again, they're used between the switches so that the VLANs so the devices that are part of the same VLAN can communicate between multiple switches. So you don't have to use different VLANs on different switches. You can use the same numbers if you want to provide end-to-end communication. You just want to make sure that the frames exchanged between the switches are tagged, so the other switch knows what VLAN the frame should be sent to. Now, the problem with VLANs and trunking is that you can have multiple paths, multiple trunks configured on different switches, which is gonna allow which is gonna build multiple paths, multiple physical paths that can be used for communication between the devices connected to the same VLAN. Like we can have a, let's use the same topology here. So Catalyst 1 on the left. Now we will have Catalyst 2 over here. We will now have two trunk links between them. So let's say you want to add some redundancy to the design, and just one PC over here and one over there. So they are obviously, those PCs, they are part of the same VLAN, say VLAN 10, it doesn't really matter. What really matters here is that we have two trunk links between the switches. So now think about the situation when a PC1 sends a broadcast frame, such as a ARP request frame. So how is the frame going to be forwarded? The Cat1 is going to get the frame. It sees this is a broadcast packet. It is going to send it over here and over there. So literally out of any interface, out of every interface except the one it got the frame on. So it got the frame over here, it will send it out of every other interface. So Cat1 is going to get the frame over here and over there on two interfaces. This is a broadcast frame. So let's say that the first one was received over here. It is going to send it down to the PC plus to any other port which is not that one. Because I received the frame on, let's say, FO2, so I'm going to send it everywhere except FO2. So it is also going to send it over here. Now another frame comes in over another trunk. Catalyst 1 sends it over here to the PC and also over here. So Cat1 gets the frame, gets the same frame over here, sends it here, and then over there. And we see that a single frame that was generated by PC1 starts looping forever. The PC1 got the frame, but there is a loop in the network. This eats up a lot of resources, and there's definitely a situation you wouldn't really have in your network. So this is when spanning tree protocol comes into play. It allows you to configure the switches with multiple redundant paths, but it is going to ensure that there is only one path, one active path at a time between all of the LAN segments in a single VLAN. So it says that one path is enough for communication between the devices. You can configure more, but I'm going to block them, and I will only unblock those redundant paths when the active path fails. The interfaces goes down, something wrong happened, and the active path is no longer available. So with STP, there will be 3 different steps that will happen initially. This is called spanning tree algorithm, STP algorithm in short. The switches will have to agree on who's going to act as a so-called root bridge, and this is based on the bridge ID of the switches. The lowest number is going to win. Actually, the lower is always better in the world of STP. So let's say that we have 3 switches this time: Catalyst 1, Catalyst 2, and Cat3, and they are connected with trunks. Cat1 is gonna have a really low, it's gonna have the lowest MAC address in this network. Let's say that this is gonna be 0006.1234.1001. Then Cat2 is going to have 0, 0, 0, 6, 1, 2, 3, 4, let's say 2, 0, 0, 2, and finally Cat3 is going to use this one. 0006, 1, 2, 3, 4, 3, 0, 3. So we see that the Cat1 uses the lowest MAC address here. And this is what's going to be important in this first stage of STP algorithm that happens in the so-called listening state. So we have interconnected the switches, brought up the interfaces. Spanning tree algorithm enters into the so-called listening phase, which lasts by default for 15 seconds, and it starts, the STP algorithm kicks in. The devices try to figure out who's the root bridge, and then what ports should be blocking, what ports should be, what ports should be forwarding, and what ports should be blocked. So during that root bridge election, as I said, this is when the bridge ID is going to come into play. The bridge ID is composed of two elements, a priority and then the MAC address. Now, by default, priorities are the same, and I also assume this is the case in this topology here, which means that the device with the lowest MAC, so this gentleman is going to be elected as a root bridge. So Cat1 is going to be our STP root, which means that this causes the switch to unblock its interfaces, every single one. So this interface and that interface, that they will become designated ports, and at some point later they will be forwarding the packets. But before we get to the packet data forwarding, let's finish the discussion on that STP algorithm. So we've got the root bridge, STP root bridge. And the next step is for the remaining switches, to select so-called root port, which is an interface that is closest to the root bridge. And which one is closer, which one is further, depends on the so-called STP cost, which is by default derived from the interface bandwidth, can be also configured manually. Let's say that the cost of this interface is 6. This one uses 19. This one uses, let's say, 20. And this guy uses 20 as well. So if you think about the cost toward the root bridge in this topology here, Cat2 says my cost is to get to Cat1 is 6 via this link, FO1. Cat3 says my cost via FO1 is 19, but via FO2 is 20 plus 6, which would be 26, so this is higher than 19. I will be using this FO1 as my root port. So this is root port on Cat3. FO1 is going to be also root port on Catalyst 2. There is just one root port per switch. On a switch that is not the root bridge. On the root bridge, all interfaces become the designated ports. So on all other switches which are not root bridges, there's going to be just one root port per device. So this is the second step of the STP algorithm. There's also a third one, which is used to figure out what ports should become the designated ports on non-root switches. So Cat2 and Cat3 in this case. So they will have to figure out basically which of them is supposed to send frames onto this segment? Is it going to be Cat2 or Cat3? And this is also based on the cost to the basically the device with the device that is going to be selected here is going to be the device that forwards the lowest cost PPDUs onto the segment. So also based on the cost, STP cost. So Cat3 is going to be sending the frames with a cost of 19 versus Cat2 is going to be sending the frames with the cost of 6. So 6 is definitely lower, which means that this interface is going to become a designated port. And finally, all other interfaces that are not root ports, not designated ports, they are going to be blocked. So this port is in the blocking state. So initially, since all of the devices were interconnected with each other, there was possibility for a loop, like PC3 is connected to this guy here, PC1 is connected to PC2 is connected to Catalyst 2. Before STP kicked in, it was possible for the devices to communicate with in this direction, or maybe between Cat2 and Cat3, with STP fully converged. When PC2 wants to talk to PC3, the only path that the packets will take is going to be through the root. Because this interface, once again, this port FO2 on Cat3 is blocked, the interface that is put into the blocking state will never forward the data packets. So the designated ports and the root ports, these are the only ones that forward the data packets. Now the question is, how long is it going to take for the STP algorithm to fully converge and for the packets to be forwarded through the network? So as I said, the listening phase lasts by default for 15 seconds. Once the STP algorithm finished its job, 15 seconds elapses, we've got the next STP phase called learning, which also by default lasts for 15 seconds. Now here the device has already figured out what port is blocking, what port is designated or a root port, and they will start populating their CAN tables based on the MAC addresses of the frames received by the switches. So the switches will be getting the data frames, they will be populating their CAN tables, but the frames will still not be forwarded. Only after that next 15 seconds elapses, the switch state, the STP state, is going to change to forwarding, and this is when the data packets will be finally allowed to go for the switches, for the switch ports.